All right, I don't remember my old Scratch account, but let's make a new project. Okay, let's start with some physics. In our control loop, we want to keep track of two things for the physics: the force applied and the velocity of the object. The position of the cat is going to be kept internally by Scratch, so we don't need to create a variable for that. Now, on every loop, we'll change the velocity by the force. And also on every loop, we'll change the x value by the velocity. Keep in mind that everything here will be in the x-coordinate dimension. Now, to make things consistent, we'll add a wait timer so that everything happens roughly every 30th of a second. So let's make some initial conditions. When the program is started, we'll set the force to -1, and we'll set the velocity to 0. We'll also set an initial position 200 units to the right. So now we've got a force acting on the left, and in this case, velocity continues to decrease. For now, we'll set force back to 0 as we figure out our PID loop. The next thing we have to do is calculate the force every tick, because the force will be changing. So we'll use this to set the force to be something. And what is that something? The first part of the PID loop stands for proportional, which means that the more the error is, in this case the error is the distance of the cat from the center, the greater the force should be. We'll set that to be the proportional constant times the x position. And for now, we'll set the proportional gain to be something small. We'll call it 0.1. However, we've left out something important, which is that when the error is positive, we want the proportional correction to be in the opposite direction. So we've got to multiply our proportional gain by -1. Now when we start the program, we can see that the cat is trying to get to the center. But the problem we see here is that it's seeming to oscillate between 2 points. And what we've actually done is define the differential equation for a simple harmonic oscillator. The cat is trying to get to the center, but as it's going towards the center, the velocity is still some number as it crosses 0, while the force is continually pushing it to the left while it's on the right side, so that it has some velocity at the center and overshoots, and then the cycle repeats back and forth. So the solution to this problem comes from the third part of the PID loop, which we'll do next. The third part, D, stands for derivative, which takes the derivative of the error and adds a corrective factor depending on that. So how will this help? When the cat is moving towards the center, its derivative is negative because its final position minus its previous position in a small chunk of time divided by that time will be a negative number. So we want the faster the cat to be going for there to be an opposite force to slow it down. And that'll try to cancel out that overshooting that we see at the center. So to calculate this, we'll need to calculate the derivative. And to calculate the derivative, you need a function. But we don't really have a function for the exact motion. All we have is the positions in which the cat has been. It's not a continuous line. So what we can do is we can track all the recent positions of the cat in a list. I don't actually think they had lists when I was using Scratch back in the day, but here we go. So in every point in the loop, we're going to want to insert the x position at the first position of this variable we'll call history, which stores the past positions of the cat. And just for some bookkeeping, we'll also add a condition to prevent this list from getting too big. So, oh man. So we'll add the condition if the size, if the length of this list is greater than, we only need 2 elements, so if it's greater than 2 elements, then we'll delete item number 3 from history. We run the program and we show history. We can see that we've got 2 updating values. I think these are extraneous from before, so we'll also say delete all when the program is run. So now we've only got 2 tracked items. So now to calculate the derivative, we take the formula, but we don't need to calculate the limit in this case for the derivative. It's just the last 2 to get an approximation at that point. So we can set derivative to be the so we can set derivative to be item 1, which is the most recent in history, minus item 2 in history, and then we'll divide that by the time difference. So I'll enable this. So now we'll add this corrective factor to our force here. I'll leave a space for the integral gain that we'll put in the future. Oops. Should be derivative, so we'll add those. So what seems to be the problem here? Oh, our gains are enormous, so we'll only need to be about 0.1 and negative 0.1 here. You can see that it stabilizes near the center without the ringing. If we loosen this gain on the derivative factor, we can see there's some shake as it overshoots the first time but slows down enough to be caught. If we lower it even more, then there's even more vibration. And so you would think everything is good now, but what happens if there's an external force? So let's say there's an external force of just 10. It's too extreme. Let's say 5, 3, 2, 1. Let's say there's an external force of 1. You can see that the desired position should be in the center here, but the actual position of the cat is at about 100. And this is because the external force cancels exactly out with the proportional gain, and because the derivative isn't changing, or the derivative is 0 in fact, because these 2 values are the same, there's no input from that factor. So the cat will settle at a position that's off from the center. And this is not what we want in a real life system. We want the cat to be exactly where we told it to be. So what can we do for this? And this is where the integral gain, or the integral factor of the PID loop, comes in. So calculating the integral is you need to take the function and you need to sum up these discrete intervals because, again, we don't have a function to use. But in this case, we'll need more history to sum up to get our integral. So I'll change this to 10. So now we have 10 numbers that we keep track of. And every time we update the x position, we're going to sum that to integral. So we're going to change the integral by the x position. And then every time we have too many, we need to take out that event. So that's the 11th event. And then we're going to take that off of the integral. So we'll need to subtract the 11th item. Okay, so now we just need to add this term back in. we'll do this. We want to keep our external factor, so we'll just put here, addition is associative and commutative. So we can set that in there, and then we add our proportion, our integral gain times our integral in here. And I think just to follow the pattern I've been doing before, I'm going to put that like this. So now we can see that when we add this term, the cat corrects itself a little bit closer to the center. So we can re-enable this, and when we slightly increase the integral gain, we get closer to the center. Maybe we also want to increase the proportional gain so that there's more force pushing it towards the center. And PID tuning is just about finding these three gains that allow us to quickly adjust to when we want the cat in a new place. One thing to note is as you increase the integral gain, there's a tendency to overshoot because it builds up the history as a factor in the force. So setting this too high, while it will help with a constant offset, can also run into problems with ringing around your desired position. So if I move my desired position, which is the same thing as just moving the cat to a new position, there's going to be some bouncing around. And that was about it. I'll link this project in the description if you want to play with it, but you can also just build it for yourself. It wasn't too bad. Yeah, that's it.